Today we're going to talk about Newton's laws. I'm Caitlin.
I'm Christina.
I'm Megan.
And I'm Karina.
I'm going to demonstrate Newton's first law in order to have a better understanding. Newton's first law states that an object in motion will remain in motion unless acted upon by an outside force. An object at rest will remain at rest unless acted upon by an outside force. Now, what does this all mean? I have placed this car in front of me, and as you can see, it is not moving. What can we do to make the car move? Well, I could push it myself and act as a force, or the wind could push it as well. However, there's currently no forces acting on the car. Now I will push the car and it will move. The object is currently at rest, but I'm acting as a force to change that. As you can see, the car was in motion for a bit, but then it came to a stop. What forces caused it to stop? The textbooks at the end of this table acted as a force to stop it. Now, what would happen if the textbooks weren't there? Would the car keep going forever? Let's find out. As you can see, the car eventually stopped. What forces cause the car in motion to go back to rest? Friction. There will always be some sort of force acting on an object when it changes from motion to rest, or vice versa. And that's Newton's first law.
Hi guys, today we're going to learn about Newton's second law, which is force equals mass times acceleration.
Okay, before we get started, we're going to talk about what each of these words mean. So to begin with, force is the strength that object hits another object with. Mass is going to be your amount of matter, and then acceleration is your change in velocity. Okay, we're going to learn about this law today by doing an experiment called crater pits. We're going to do 3 different balls. We're going to drop them in a pit of like flour and cocoa powder and sand, and the mass of them is all going to change the size of the crater pit. So this is going to show you how mass and acceleration affects the force and the size of the crater pit.
So while we're doing this, we want you to please keep in mind and think about these questions. Do you think there will be a different size pit for each size ball? And what are the forces that are acting on the marble?
Okay, so let's begin. The first thing we're going to do is we're going to pour a layer of sand evenly over the aluminum pit. We're going to kind of shake it out so that it's even. Kind of spread it. Okay, the second thing we're going to do is we're going to take this flour and do another even layer. We're doing all these layers so you can see how deep the pit is when you drop the different size balls. Okay, so now we're going to put a layer of cocoa, and the reason we do this is because it's darker, so when you drop the balls, you'll be able to see the indentions that the balls make better. Perfect. Okay, first it's important to note that acceleration on Earth is constant. It's about 9.8 meters per second squared, and that's because of gravity. But we're still going to drop it from the same height. We're going to drop it a meter above the pan. And we're going to drop the balls all from the same height. So the first one is the styrofoam ball, and this is going to be the lightest, so the mass is the least. Go.
1, 2, 3.
Oh, let's try that again. Do it more, maybe like over here. Yeah, there you go.
2, 3.
Okay, perfect. And then the second one's the marble, which has the second highest mass. Okay, and then the last one is this magnetic ball, which obviously has the biggest mass. Okay, perfect. Now if you look here, we're going to take the balls out. The first one is the styrofoam. So this one made kind of like a shallow indentation, but definitely not the biggest. Here's the marble. It's kind of hard to see. We want to be careful not to disturb the pit too much, but it kind of went down there. So it's like that much. And then the last one is the magnetic ball, which obviously made the biggest pit.
As you can see, the magnetic ball created the deepest crater. This proves, since acceleration is always constant on Earth, that the mass of the magnetic ball was increased, and that was strengthening the force, proving Newton's second law.
For this demonstration, we will be working with Newton's third law, which states for every action there is an equal and opposite reaction. We must first think about what this all means. So what exactly is meant by equal and opposite reaction? The simple answer to this is that in every interaction there is always a pair of two forces acting on the interacting object. The size of the force of the first object will equal the size of the force of the second object, and their directions will be opposite. For this demonstration, I have taken another student and we will both be pushing on this cart to demonstrate how our forces balance out. As we begin pushing on the cart, you can see how it's not really moving because our forces are being equalized. Had our forces not been equal, you can see how the cart begins to move towards me. After this demonstration, we have been able to observe two things. The first is that we can see how forces push and pull upon each other. Second, we can see how one force balances out the other as they exert the force from each other. And that's Newton's third law. Thank you for watching.